Cool.
Yes.
Okay, thanks. Hello, everybody. My name is Ben Lazarine, and today I'm going to be leading our talk on identifying vulnerable GitHub repositories in scientific cyber infrastructure. For a brief overview of the presentation, we're going to begin by providing some background and research questions of our project. Then I'll go into the data collection and proposed methodology, and we will conclude with selected results of our work. So again, my name is Ben Lazarine, and I'm a PhD student at the Kelley School of Business at Indiana University. And my collaborators for this work are Edwin Skidmore, who's the Director of Infrastructure for Cybers at the University of Arizona, and Dr. Sagar Samtani, who's an assistant professor at the Indiana University. Edwin is going to be helping me co-host this presentation, discussing how our work is most relevant to Cybers at the end of the presentation. And Dr. Samtani will be helping field Q&A in the comments of this Zoom session. So for a brief overview of our project, which falls under proactive cyber threat intelligence and comprehensive network monitoring for scientific cyber infrastructure, this actually falls under the NSF's Cybersecurity Innovation for Cyber Infrastructure initiative. Our project has 3 objectives, and for the scope of this presentation, we're going to be focusing in on the second objective for conducting a vulnerability assessment of scientific cyber infrastructure assets. In order to frame the assessment of CI assets, we first present 5 major asset categories that are relevant to our objective. These include instruments, facilities and hardware, systems, software, and configurable technologies, and scientific CI data. As you can see, each of these categories is comprised of multiple subcategories, and we have identified 2 categories that scientific CIs are increasingly relying on in order to support their operations: configurable VMs and code repositories. Configurable VMs are virtual machines that can be customized and shared easily between researchers, such that researchers don't have to deal with the lengthy process of setting up a virtual machine environment, downloading all the necessary packages, and dealing with a bunch of dependency issues every time they need to begin doing their work. Code repositories are repositories that are hosted on platforms like GitHub and GitLab, and they are ways for researchers to share code and collaborate on code quickly and easily. Some of the benefits of utilizing code repositories is that it increases research speed, it increases research transparency, and it is easier for scientific reproducibility to be conducted. In order to dive deeper into what social coding repositories look like and the types of vulnerabilities that they contain, we present a screenshot of an actual code snippet within a GitHub repository that contains a vulnerability. When visiting a GitHub repository, there are a number of useful pieces of information that you can immediately find. First, you'll be able to see the name of the owner of the repository and the name of the repository itself. Additionally, you'll be able to see how many times the repository has been forked. Forking is a really cool feature on GitHub that allows one user to copy the repository from another user's account into their own. Then once a user has forked that repository, they're able to modify that version of the repository without it impacting the initial repository that they copied. In our screenshot here, we illustrate an example of a code snippet that contains a shell injection vulnerability. The presence of insecure coding practices like this on social coding platforms can lead to the spread of vulnerabilities that can disrupt scientific cyber infrastructure operations. So now that we've introduced the types of critical assets that we're concerned with in this presentation, we're going to briefly go over the vulnerability assessment tools available to us to scan these assets accordingly. Existing vulnerability assessment tools can be grouped into 4 categories. There's general purpose, web application, network traffic, and code analysis tools. We leverage code analysis tools for our assessment. However, the utilization of these types of tools, especially in a GitHub environment, can return thousands to millions of results. So this necessitates the development of novel approaches to be able to process these large amounts of results in order to automatically identify, categorize, and prioritize vulnerabilities present in GitHub repositories. In a review of social coding repository research, it can be seen that past studies primarily focus on just general analysis, including works like cross-platform user identification and the identification of key users. Additionally, we can note that the nature of the user-repository relationships on social coding platforms such as GitHub lends itself well to network analysis, and this can be reflected in the network science-based methods that are primarily used in this area. However, we also note that little work has been done to combine both a network analysis assessment with a vulnerability assessment. From our review of critical CI assets, the available vulnerability assessment tools at our disposal, and existing social coding repository literature, we can see that the current level of scientific CI's use of social coding platforms in both the number of repositories and the level of development activity across them is at a scale and a scope that necessitates the development of an automated approach to be able to efficiently group together repositories that have similar vulnerabilities such that they can be prioritized for remediation. Fortunately, recent advances in the use of deep learning to generate graph embeddings can be leveraged for this grouping task. In the remainder of this presentation, I'm going to present our framework that aims to group repositories that have similar vulnerable landscapes within them through the use of a novel deep learning method such that we can process the results of our vulnerability assessment efficiently. Two key aspects. Now that we'll move on to discussing our research gaps and questions, our data collection, and our vulnerability assessment and our post-research graph embedding method. Here you can see that our research design is comprised of 5 components. The collection of the GitHub data is the first component from multiple scientific cyber infrastructures with a subsequent vulnerability assessment. Then we represent both the results from our collected GitHub data and our vulnerability assessment results as a graph that can be operated on by our proposed graph embedding method. Lastly, our research design concludes with 2 experiments to evaluate the quality of the clusters of our graph embedding method enables us to generate, as well as a case study to demonstrate the practical use of our framework. Our GitHub data collection is comprised of all collectible GitHub data that is generated by 2 selected large cyber infrastructure organizations, as well as any data relevant to users who have utilized any of these repositories. The 2 selected CIs for our collection are both federally funded and support hundreds to thousands of universities in research ranging from life sciences to atmospheric research. So here we provide an overview of the actual data within our collection. As you can see, across the 2 scientific CIs that we identified and collected, we identified 835 root repositories and 2,052 fork repositories. For the remainder of this presentation, whenever I'm referring to a root repository, that will refer to a repository that was actually created directly by the cyber infrastructure organization themselves. And whenever I refer to a fork repository, this is an instance of a repository that has been generated by another user outside of the CI organization forking a root repository. Across the 2 CIs at the time of collection, there have been 389,000 commits made to the collected repositories by about 5,000 users. Additionally, there's a notable difference between the 2 CIs, both in the number of repositories that they have generated and the level of activity that we've seen across them, with CI number 2 being much higher in both of these areas. While the 2 CIs differ in their size and activity level, they do share 2 top languages of C++ and Python. The top languages that we identified in our collection subsequently motivate the types of vulnerability assessment tools that we select to scan them. So based off of the requirements of our GitHub data collection, we selected 4 current vulnerability assessment scanners to cover key languages, as well as scanners that are capable of leveraging key attributes of GitHub data. We selected Bandit to be able to scan Python files, FlawFinder to scan C and C++ files, and additionally, we selected GitRob and TruffleHog as scanners that are capable of integrating directly with GitHub to scan full repository histories for any potentially leaked secrets that they contain. In Table 5, we present a hierarchical breakdown of the types of vulnerabilities that we include in our assessment. As you can see, the vulnerabilities at the highest level are grouped into secrets, insecure code, and code that is vulnerable to attack. You can also clearly see the coverage of each selected scanner across all 14 types of vulnerabilities that we've identified for assessment. So now that we provided a summary of our GitHub collection and an overview of our vulnerability assessment tools, we're going to get into the actual results of our vulnerability assessment. Our vulnerability scan overall returned 1,484,000 vulnerabilities, with 1,415,000 of these vulnerabilities belonging to cyber infrastructure number 2. While the vulnerabilities vary quite drastically between these two CIs, it's actually interesting to note that the distribution of these vulnerabilities is quite similar. They both follow a distribution where over 80% of the vulnerabilities identified are low severity and only around 3% are high severity vulnerabilities. Another interesting key takeaway from our initial results is that the majority of the top vulnerable repositories that we identified are forked repositories. And this illustrates that the forking capabilities of GitHub actually leads to the propagation of vulnerabilities across the GitHub ecosystem. To structure our collected data for subsequent analysis, we represent it in the form of a graph. GitHub data follows a bipartite network structure that lends itself really well to being able to be projected into two monopartite networks to identify key users and repositories. A bipartite network is a network that has two distinct types of nodes, and every edge in this network only connects nodes of different types. Therefore, we define our graph as G equals U, R, E, F, where G is our directed graph, U represents the node set of all the users, R represents all of the repositories, and E are all the edges connecting a user to a repository, which represents anytime a user might have made a commit to a repository in our collection. Lastly, F is the feature metrics of each node, which represents the number of vulnerabilities from each user or repository in our collection. We then are able to project this bipartite network into two monopartite networks. To illustrate what this means, for our repository monopartite network, any edge in this network represents an edge between two repositories, essentially means that in our bipartite network, there was one user that had made a commit to both of the repositories that are now connected in our monopartite network. Given the focus of our study is specifically on grouping vulnerable repositories, we leverage only the repository monopartite network for our subsequent analysis. So out of all the graph embedding methods that we identified that were able to satisfy the requirements of our clustering task, text-associated deep walk was a method that we identified as performing best at being able to account for high-dimensional feature vectors. In our context, that meant being able to embed over 40 types of vulnerabilities that we associated with each repository. However, TDW was unable to weight input features to account for varying importance to the embedding. In our context, these importances are driven by the severity of vulnerabilities that are being embedded. Low severity vulnerabilities and high severity vulnerabilities should not be treated equally during the embedding generation process. Therefore, we designed a novel vulnerability associated deep walk, VADW. The aim of our VADW novelties is to enable VADW to prioritize high severity, low quantity vulnerabilities over low severity, high quantity vulnerabilities to ensure that the generated embeddings that our model returns are capturing the repository vulnerability information how we want them to. So now that we presented our data collection and proposed method, we will go into our selected experiment results and case study. To conduct our evaluation of VADW, we benchmark it across 4 state-of-the-art unsupervised graph embedding models that are capable of accounting for nodal features. We used 2 experiments to evaluate the performance of VADW, aimed specifically at evaluating the quality of the clusters that VADW enables the generation of. The experiments were designed to emulate a clustering task that a security analyst would use VADW for. First, we evaluate VADW's performance across all repository types. This experiment evaluates VADW's ability to represent both root and fork repositories. Second, we evaluate VADW's performance when only taking in root repositories. The purpose of this experiment is actually twofold. First, it is critical to ensure that VADW can perform well when representing repositories that are directly generated by Cyberinfrastructures alone. And second, by removing root repositories, this actually greatly increases the vulnerability variance that is seen in our network of repositories. And so this experiment captures how this increased variance affects VADW's performance. Here you can see the results of our first experiment. We used 5 cluster evaluation metrics to demonstrate the performance of our model. However, the measure that we're most concerned with in our context is V-measure. And as you can see, VADW outperforms all 4 variants in V-measure for both Cyberinfrastructures. These results indicate that VADW outperforms existing models when capturing and representing critical vulnerable repository features. To take a bit of a closer look at the implications of VDW's improved performance, here we highlight an example of a high severity repository that was correctly labeled by VDW that was missed by other models. This repository contains a high severity file permission vulnerability that previous models would have missed. Being able to accurately identify and group these types of vulnerabilities is critical to enabling cyber infrastructures to execute targeted remediation. Here we present the results from our second experiment, and as you can see in this experiment, VDW outperforms all 4 variants in this experiment as well. And again, for this experiment, we highlight another example of a high severity repository that was correctly labeled by VDW while incorrectly labeled by TDW. In this instance, it's important to note that these findings for experiment number 2 are immediately actionable by cyber infrastructures because the vulnerable repository that we've identified is one that is under the direct control of a CI. So now that we've demonstrated VDW's performance against benchmark methods, we will demonstrate a more practical value that VDW offers for cyber infrastructures as well as cybersecurity professionals through our case study. So once a security analyst has conducted a vulnerability assessment and then used VDW to process the results of that assessment, this is an example of the results that they would be returned with. So as you can see, figure 8 shows a graphical depiction of what repository clusters might look like. And we have selected 2 to highlight that contain a high amount of vulnerable repositories. As you can see, cluster D contains repositories that have both secret vulnerabilities and insecure functions. These vulnerabilities have security implications for this cyber infrastructure's web portal that provides access to both their data store and their compute resources. Second, cluster I contains repositories that process user input insecurely, have insecure functions, and have file permission vulnerabilities. These vulnerabilities have security implications for this CI's data management software. So through our process of using VDW to generate clusters from a vulnerability assessment, we are able to analyze the clusters to identify groups of repositories with similar vulnerabilities that can all be addressed with targeted mitigation strategies. A key benefit of this process is that mitigation strategies become generalizable across multiple repositories in a given cluster. In addition to identifying clusters of vulnerable repositories, we also present 4 types of vulnerabilities that we've identified. First, secrets, file permissions, insecure functions, and insecure inputs. Some of the potential threats that these vulnerabilities actually pose to cyber infrastructures include things like abused cloud computing resources, allowing malicious files to corrupt file systems, allowing attackers to modify a file before it is opened, and malicious remote code execution. A couple of remediation tactics that can be used to address these vulnerabilities are the discontinued use of all leaked secrets present on GitHub, and patching vulnerable code snippets, and alerting repository users to update to the latest repository version. So in addition to addressing existing CI vulnerabilities through targeted mitigation, our work also aims to provide CIs with strategies that they can use to mitigate how many vulnerabilities are introduced onto their platform in the first place. These strategies include things like informing CIs about the types of vulnerabilities that can be present on GitHub, informing users about how practices such as forking can lead to the spread of vulnerabilities, holding CI workshops, and then developer training to help train software developers about how the use of GitHub can actually lead to the spread of vulnerabilities. So in conclusion, scientific CIs use social coding repositories such as GitHub to facilitate the development of open source software. And while this has many benefits like increased research speed, it also leads to the propagation of vulnerabilities that can be used, that can expose scientific CIs to cyber attacks that can disrupt their research. Therefore, in this study, we developed a novel VDW approach that is capable of automatically identifying and clustering repositories on GitHub with similar vulnerabilities. Lastly, targeted mitigation or remediation strategies were proposed to help CIs address vulnerabilities within selected clusters. I'm now going to hand the presentation over to Edwin so he can discuss promising future directions and how this research is most relevant to Cyverse.
Hi, everyone. So some future directions are that we want to apply VADW to look at the commit level for the repositories, identify how vulnerabilities propagate across repositories. So some of that is not just as people fork, but also how they may propagate as users use other social coding repositories. Also, as users, introduce vulnerabilities either through tool creation or workflow creation, then potentially targeting them for security awareness trainings, and then grouping some of these these vulnerabilities as into categories for the different scientific domains. So in any case, so one of the goals for VADW is essentially operationalizing it into a scientific CI that's in production. For Cybers, that means incorporating these assessments or looking into incorporating these assessments into Cybers' middleware and user interfaces. So, for example, as researchers create tools or create workflows, then leveraging VADW to analyze these tools and workflows more on demand. So initially, these assessments would only be exposed to the system operators for cloud or the tool or workflow, or to the tool and workflow creators. And this would be best so that these are the individuals who could take action or mitigate these issues. In other areas that we would like to see VADW go is, as I mentioned before, scanning across other code repos. GitHub certainly isn't the only code repository. GitLab and Bitbucket are certainly popular, but also being able to scan private repos in some way. So lastly, the research presented here focused on virtual machines. As a lot of people know, virtual machines is only one type of a compute environment, and certainly VADW isn't restricted to virtual machines. But where Cybers is going is we support containers and container orchestration and even infrastructure as code templates. And so I think this would be a good application for VADW. Okay, next slide. So thank you everyone for attending our presentation.
I think at this stage we can open it up to any questions that from the audience related to our talk.
So there's a question: has Cybers fixed the high severity vulnerabilities? Yeah, so this is certainly an ongoing thing. There's always new things. So VADW is certainly one tool that we leverage, and we also have other tools that we rely on. But yes, we do try to address this high severity vulnerabilities as we get them.